Hi everyone, make sure we're being taped, yep. Okay, so now we get into this thing called eigenvalues. And it's really kind of a simple notion, but it's very powerful. So let me explain what they are. I'm not going to write down everything that's in the book. I'm going to assume that you have the book and you're kind of following along, and I'm going to kind of add to it and do things kind of along the same lines, but not just write things down. So here is where we are. We've got ourselves a vector space, and we've got ourselves a linear transformation T from a vector space to itself. Okay, so notice that this is the same vector space as this. So the domain and the range are the same one. And a eigenvector and an eigenvalue are things that have this property. If you take a particular, I'm going to call it x naught, just to indicate that it's a particular vector in your space, x naught, and you take t of it, and you send it over, and you take t of it, if it turns out that when you stick this into the function, you just get a constant times that vector, okay? That's the key. You're just getting a constant times that vector. Then this thing is said to be an eigenvector, and this is said to be an eigenvalue associated with that vector. Okay, so that's the idea. Let me give you an example of something from a world that you know. Suppose that v is differentiable functions. Okay, functions that you can find the derivative of. So that's our vector space. I think we showed back in an earlier section that that was a vector space. And suppose that t of any, I'm going to call it f now, because if they're functions, then my vector is going to be the function f. Suppose that what t does to f is it takes its derivative. That's what it does. So it takes the derivative of them. Okay, so we showed earlier that that's a linear transformation, because what are the two things you have to show? That t of f plus g, let's just remind ourselves over here again. T of f plus g is equal to f plus g, the derivative of it, but we know that if you take the derivative of the sum, that's the sum of each one, and that's equal to t of f plus t of g. So that's one thing that has to be shown to be a linear transformation. And the other thing is that t of some constant, let's just let c be the constant. Then this is c, the derivative of c times the function f. And we know that the property of derivatives is such that that's just c times f prime. And c times f prime is c times t of f. So both of those things are satisfied, which means that's a linear transformation. Okay, so that's a review of what we've done before. So what would be a let's find all the eigenvectors that are associated with the eigenvalue lambda. That's the way I write a lambda. So if this is going to be equal to lambda times f, if t of f, which is f prime, if that's going to be equal to lambda times f, then what does f have to satisfy? What is a function such that when you take its derivative, you get lambda times that function? Well, this ends up just being in fact, if I were to, instead of putting an f there, if I were to write it as the function y, then it might even look a little more familiar to you. There's what it does, is it takes the derivative, and if that is equal to lambda times y, then what kind of a function does y have to be? And this is just a function something that you know how to solve, hopefully. Lambda x, and or lambda dx rather. And so you take the antiderivative of both sides, and you end up, by the time you're done, with this is going to be equal to a e to the lambda x. So it turns out that if lambda is your eigenvalue, then you've got an infinite number of eigenvectors, all of this form, which are associated with that eigenvalue. Because I say an infinite number, a can be anything you want, right? A could be a 2 or a 7 or a pi or a e or a 17 or a 0. Could be anything you want. So there's an example of eigenvectors and eigenvalues in the world of differentiable functions. Okay? So, by the way, we do have one restriction. To be an eigenvector let me write it this way. We don't accept 0, the 0 vector, as an eigenvector. And the reason we don't is we're interested, because 0 would be true for anything, for any linear transformation, and for any value of lambda. It's true that t of the identity is going to be equal to this, because we know that t of the identity gets sent to the identity, and 0 times the identity is the identity. So sure enough, that's true. So it's trivially true. It's the 0 vector is always going to satisfy this. So when we say, does something have an eigenvector? Well, if 0 was an eigenvector, then everything would have an eigenvector. So we're interested in ones that have things other than just 0. So that's why we don't even call 0 an eigenvector, so that that way if we say, hey, does it have one? We're really interested in ones that aren't equal to the 0. Okay? So let's look at some other examples of eigenvectors. Let's suppose that we are on the plane, which I'll write as R2, going to the plane. Okay, so here's R2, and so something in R2 is going to be a vector like that, right? You can either write it as xy like this, or you can write it as x comma y like that. I'm going to write it like that just to be clear that this is a column vector, but there's your point xy. And let's look at the ones in the book. Suppose that we're concerned that we I guess I write them like this in the book. So let's look at 4 different ones. Let's look at t of xy gets sent to x minus y. Okay, so here's xy right here, and this vector gets sent to this vector. Okay, so xy gets sent to x minus y. There's x minus y right there. See that? So this one gets sent to that. Well, it's certainly not the case that that's an eigenvector, because to be an eigenvector means that this thing is sent to what? It's sent to a constant times itself. So to be sent to a constant times itself means that it's sent to some multiple of itself, something that's either along here or along there, but something like that. But this vector, notice, has a whole different direction to it. So this particular one is not. But notice that that this vector right there would be an eigenvector. See that? If you take t of x0, which is that one right there, that's going to get sent to x0, which is 1 times x0. See that? So anything along the x-axis there is going to be an eigenvector, because if you stick it into this function, what does this function do? It takes your y value and turns it into the negative of it. And so if you were here, it would put it up there. It always just changes, it takes it to the negative, whatever the y value is, it takes it to its opposite one. So this vector becomes this vector, okay? So everything along this line is going to be an eigenvector with an eigenvalue of 1, because this thing is just equal to 1 times itself, okay? Here's some other eigenvalues. Everything along the y-axis just gets sent to its opposite. See that? This one here is going to get sent down there. So t of 0y gets sent to 0 minus y, right? That's what this says to do. It says that x stays the same and y goes to negative y, so this goes to this, and notice that that is just negative 1 times 0y. See that? So t of it is negative 1 times the original vector. So all of these along here are eigenvectors with an eigenvalue of negative 1. Okay, so that's it's called I think I call that the reflection. Called the reflection that reflects this one like so. Okay, you can come up with a similar one that reflects this way. Okay, so that's all number 1. Number 2 is one that does this. It sends every vector to its projection on the x-axis. So this one here comes right down there. That's what it does. This one here gets projected right there. So it just projects it up to the x-axis. So it takes this vector and turns it into this one. Okay? Can you find some eigenvectors and eigenvalues for this particular linear transformation? Notice that anything along the x-axis is going to just get sent straight to itself. See that again? So t of x0 is going to be x0, which is just 1 times x0. So it just gets sent to itself. So everything along here is going to be an eigenvector, where the eigenvalue is 1. And everything along here, what happens to everything here? It gets projected straight down. See that? It's going to get sent to 0, 0, which is just 0 times 0y. So everything along the y-axis, everything like this, everything along the y-axis is going to be an eigenvector where the eigenvalue is equal to 0. See that? So there's that one. What about this one? What about the one that moves that rotates everything 90 degrees? So it takes any vector that you have here and it just rotates it 90 degrees. So this one here, let me make it look like this instead. Okay, here's your vector xy. It's going to rotate at 90 degrees, so it's going to look like this. See that? It just rotates everything 90 degrees. So there, I think you can convince yourself there's no vector there that's going to be an eigenvector, because every single thing changes its direction. It's not, nothing ends up being a multiple of what you started with. Okay? Everything is in a totally different direction, and nothing is a multiple of what you started with. Okay? How about this one? How about t of xy is equal to negative x, negative y? So now what it does is it takes every vector and it sends it in exactly the opposite direction. Okay? Notice that is going to be negative 1 times xy. So any vector here, any vector in all of R2 is going to be an eigenvector with the eigenvalue being negative 1, because no matter where you start, by the time you stick it into t, you're going to get -1 times the one you started with. See that? So each thing here, it's just some constant times the one you started with. Some constant times the one you started with. That's what you started with. A constant times the one you started with. Okay? So so there. We could do one more. One that's not in the book. What if we make it 3x, 3y? Okay, what does that do? That takes every vector you start with, and what does it do? It just multiplies it 3 times as far. So that's going to be just 3 times xy, and so that's going to be an eigen. Everything in the whole plane is going to be an eigenvector there again, and the eigenvalue is going to be 3. Okay, so there you go. Okay, now, those are all examples to help you understand eigenvalues and eigenvectors, but where we're really going to concentrate our attention is we're going to concentrate on our attention on linear transformations that look like this. And x now is going to be something of this form. It's going to be something in R2 of the form xy. So I'm going to put an x with a hat over it to indicate it's the vector x. It's going to be xy. And that'll follow what I have in the book. And so t of x is this. It's 1, 3, 4, 2 times x. Okay, so in other words, I could have written it like this as well. I could have written it t of xy is equal to 1, 3, 4, 2 times the vector xy. So there's your vector, there's your vector. And this thing is a linear transformation. Let's first of all just show that it is, okay? Why is it? Because if I take two different vectors, x1, y1, plus x2, y2, then what does this say to do with it? It says to take 1, 3, 4, 2 and multiply that by the vector x1, y1 plus x2, y2. And I'm not going to go through all the details, but basically you can add these together and do all this to it, and by the time you're done with it, you can show that that's going to be t of x1, y1 plus t of x2, y2. Okay, everything just it's all the distributive property works, and you can show that. Same thing with multiplying it by a constant. Okay. In fact, I think we earlier on in the book we actually showed that that was a linear transformation. So that is a linear transformation. So let's see once if we can find some eigenvalues for it. And here's the question that I have in the book: is x1 equal to 3, 5? Is that an eigenvector? And is x2 equal to 6, 8? Are those things eigenvectors? So let's give it a try. Let's put each one in there and see what we get. 3, 5, 1, 3, 4, 2. And you put in 3, 5, and we know how to multiply matrices now. What do we get? We're going to get 3 plus 15 is 18. And here we're going to get 12 plus 10 is 22. And I look at that and I say, is that a multiple of this? No. You have to multiply 3 by 6 to get this, and if I multiply 5 by 6, I don't get that. So I'll say no, not an eigenvector. I'll abbreviate it like that. Okay, let's try 6, 8. T of 6, 8. Okay, so 1, 3, 4, 2. Apply that to the vector 6, 8. What do we get? Here we're going to get 6 plus 24 is 30. Here you can get 24 plus 16. What's 24 plus 16? 24 and 16 is 40. And I look at that and I say, is this a multiple of this? And I say, aha, yes it is. This is just equal to 5 times the original vector. Agreed? That's equal to 5 times this. So 6, 8 is an eigenvector. And what's the eigenvalue? 5 is an eigenvalue. Okay? So there we have that. Okay? I'm just following my notes pretty closely here. Okay, the next thing I want to show you is that let me just do it like this. Now we're going back to a general situation again. Let me write it like I have it in the book. Okay, what's this saying? It says, let me make sure you're still with me here. Okay, good. It says I collect all the different vectors for which lambda is an eigenvalue. I collect all those things together, and that's a subspace of V. Okay, so drawing a little diagram here. Here's my T that goes from V to V, and I take all the different ones such that when I take T of them, I end up with just lambda times that vector. And if I collect all those things together, that is going to be a subspace of V. And you remember, what are the two things you need to show in order to be a subspace? We need to take, if we have two things that are in there, their sum has to be in there, right? So I'm going to say let's call them, let's just call them X and Y. Let X and Y be in V. Okay, so now I'm letting X and Y both be here. There's X, that one is Y. Okay, so I need to show that if both of those are in there, then the sum is in there. So let's check it out. Then, oh no, I don't want to mean in V. They're both in this subspace. Okay, so they both satisfy this. Okay, they both satisfy that, and I need to show that their sum does as well. So let's check it out. T of X plus Y. Well, what can we say? I don't know that that's equal to lambda times X plus Y. I don't know. But what I do know is that this is a linear transformation. So since this is a linear transformation, I know that that's T of X plus T of Y. I know it's a linear transformation. Now, I know that both of these things, it just froze up on me, so I'm going to just repeat myself for a second here. So I'm assuming that X and Y are both in there, and I need to show that X plus Y is in here. So since X and Y are both in there, first of all, since T is a linear transformation, I know that T of X plus Y is equal to T of X plus T of Y. So I know that since T is a linear transformation. Now, since X and Y both satisfy this, I know that this is equal to lambda times X, and this is equal to lambda times Y. So that's true. And now I just know from simple algebra that that's equal to lambda times X plus Y. And now notice what I've just shown. I've shown that T of X plus Y is equal to lambda of X plus Y. So sure enough, X plus Y is in here, because that's what it needs. That's the property you have to be in here. You have to be the case that T of that thing is equal to lambda times that. And T of this thing is equal to lambda times that. So sure enough, that is in there. Okay, let's do what else is needed. Let's we're gonna say t of we already know that x is in there, so t of, let's say, alpha x is equal to, well, this is a linear transformation, so this is equal to alpha t of x. And now I know that x is in here, so that's equal to this. And that is equal to that. And so now I've just shown that t of alpha x is equal to lambda of alpha of x. So alpha x is in there. Okay? So we've just shown that given any eigenvalue, that the collection of all the things all the eigenvectors which are associated with that eigenvalue, along with 0, because 0 has to be part of your space as well. Even, just a second. Okay, turn off my phone. Even though we're not calling 0 an eigenvector, it still is part of this space because the 0 vector is part of every space. So anyway, so this given any eigenvalue, the collection of all the vectors that are associated with that eigenvalue form a subspace. Okay, so that's what we showed in theorem 716. Okay, that's 716. Okay. So, just to be clear, then, if you have yourself an eigenvalue right there, then this collection right there of all the vectors that are eigenvectors associated with that eigenvalue, that is called, what do I call it? That is called the subspace how do I write it? Associated with lambda. Okay, so it's the associated subspace. Given any eigenvalue, you get yourself a whole subspace. Okay? Very good. Okay. Now, we come upon the most important theorem here that's going to give us so much power. So this is theorem 718, and it says this. I'm going to grab my sheet here so that I have it. It says theorem 718. It says A is an n by n matrix. So there's an n by n matrix. We're going to be using just 2 by 2 matrices, but I just want to show you that this is true for everything. And lambda is a real number. It's a scalar. Then here's the then. Then there is an eigenpair x lambda, where this thing is your eigenvector and this thing is your eigenvalue. There is an eigenpair if and only if the determinant of A minus lambda I is equal to 0. And let's prove it to you first, and then we'll see how this is so useful. Okay? So here's the proof. Okay? So we're going to start off by assuming that this thing is an eigenpair. What does it mean to be an eigenpair? It means that AX is equal to lambda times x, and x is not the zero vector, because we know that's always true for the zero vector. So the point is, to be an eigenpair means that this is something other than the zero vector. So we'll say x is not equal to, and I use a theta here for my zero vector. Okay, so we start with that. Okay, that is equivalent to saying that ax is equal to lambda times the identity matrix times x. Remember, the identity matrix is just the one that's ones down the diagonal and zeros other places. If you multiply that by anything, you haven't changed it at all. Okay, so that's true. Okay, that's equivalent to saying you can do the same thing with matrices that you can with numbers. You can just move it over to the other side. Okay, so that's equivalent to this. Now, these are all things that are true of matrices, which we haven't talked about in this course, but in your linear algebra course where you talk about matrices, this is all stuff that is true. If you have ax plus bx, that works just like numbers. You can factor the x out the back, and you can write it as a plus b. So it has that distributive property as long as you are careful not to switch sides. Everything, both of these are on the left, okay? So that's all okay. That's something that we won't prove here, but the point is we can write that as a minus lambda I x is equal to this. Okay? And now what do we know? We know that this is true from what we did in the previous YouTube lecture. We know that this is true. Look at here. What do we have? We have some matrix times x is equal to the zero vector. This thing is not the zero vector itself. If it sends something to the zero vector, then the determinant of this thing has to be 0. The only time it sends something to the zero vector, which is not the zero vector, is if this thing here, the determinant, is equal to 0. That means it's sending lots of stuff here, more than the zero. It sends the zero vector there, it sends the zero vector there at least, and the fact that it sends this thing there as well means it's sending more than one thing to the zero vector. And if it is sending more than one thing to the zero vector, then we know that the determinant of this thing has to be 0. So there is where we made use of that previous theorem. Okay, so the determinant of that thing has to be 0. If it sends, in order for the determinant not to be 0, means it only sends one thing to this. But this thing sends more than one thing, because it sends a zero vector there, but it also sends this x there as well. So if it sends more than one thing there, then the determinant of it has to be 0. So there we have it right there. Okay? So let's see once how this is all now used to solve some key problems. We're going to be doing all sorts of them like this, and so I'll erase the board to get the whole thing. Okay, so this is example 719, and I say find all eigenvalues and eigenvectors of A equals 1, 3, 4, 2 of that matrix. Okay, so here's the method, and again I'm following along with the book, but just in case you want to see it explained rather than read it, here you go. So the first thing you do, and I'm just going to try to do it exactly the same way I have it here, is we first of all need to determine what is the determinant of A minus lambda I. Okay, now let's think about what lambda I is. I is the vector, is the matrix that looks like this. If I multiply it by lambda, then I've just got lambdas there. And now I'm taking this vector, or this matrix right here, and I'm subtracting this one. So by subtracting it, it just means I take 1 minus lambda. This 3 just stays 3. This 4 just stays 4. And this 2 is going to be 2 minus lambda. See that? So when you see this, all it means is that you subtract lambdas down the diagonal. Okay? So this is just going to be equal to 1 minus lambda. And I want the determinant of that. So let me continue on with this. The determinant of 1 minus lambda, 3, 4, and 2 minus lambda. Okay? So now it becomes a bunch of algebra. How do you evaluate a determinant again? You take this times this minus that times that. So that's going to be 1 minus lambda times 2 minus lambda, all subtract 12. See that? And now, just because of lack of space, I'm going to crunch in as much as I can here. It's going to be 2, and here's minus 2 lambda. It's going to be minus 3 lambda, and plus lambda squared, and minus 12. And now I'm going to go way over to this side because I'm going to need all the space I can get. And so this is going to be lambda squared minus 3 lambda. And then notice here I have negative 12 plus 2 is going to be negative 10. Okay? And what we want to know is what we're finding is where this thing is equal to 0. So we want to know where is this thing equal to 0. So that's what we're after. And so we want to know when is that equal to 0. And so let me write it like this. Implies this thing is equal to 0. And now I can factor that, and that factors into what? Lambda minus 5 and lambda plus 2. Right? We're trying to find out where is this determinant equal to 0. And so those are our two eigenvalues now. So it's whenever this thing is equal to 0. So it's whenever this is equal to 0, and that's going to be, notice this is a full sentence here. This sentence implies this sentence. What's the next sentence? Lambda is either equal to negative 2 or to 5. So those are your two eigenvalues. So those are your eigenvalues. We've found the eigenvalues. Okay, it's an eigenhunt. We've got the eigenvalues. Now we have to find the associated eigenvectors. So let's do each one. So for the eigenvectors, let's take the 5 and see what we get. Here's what we're after. We want to know when will this matrix times xy equal 5 times xy. There's some out there, we got to find them. Okay? When will this matrix times xy equal 5 times xy? Well, let's multiply it out and see what we get. This is going to be x plus 3y is equal to 5x. And this is going to be 4x plus 2y 4x plus 2y is equal to 5y. Agreed? So now, if we move everything over to the left-hand side, we're going to get what? We're going to get negative 4x plus 3y is equal to 0. And if you move this over, you're going to get 4x bring this over, it's going to be negative 3y, right? Subtract that, you're going to get negative 3y is equal to 0. Notice that these two equations, one of them is just a multiple of the other. So they're redundant. They're both giving us exactly the same information. So I can just get rid of one of them and just use the other one. And I'm going to do it the same way I did here. I'm going to let y be equal to t. And if y is equal to t, then what will x be? Then I'm going to get 4x is equal to 3t. And so x is equal to 3/4 t. So x is equal to 3/4 t. So that means that your eigenvector then is going to be 3/4 t, and you can factor the t out, and you're left with 3/4 and 1, and all t can be anything. So any constant times this is going to be an eigenvector. So there's no reason to have that 4 there in the denominator. We can just think of multiplying this whole thing by 4, and we can just let it be, if you multiply everything by 4, it's going to be 3, 4. And so it's everything basically where you multiply this thing by 4/3 and you get, well, whatever, yeah. Where you have that same proportion there, okay? So here's the way I like to write it. The eigenspace associated with lambda equals 5 is equal to all the vectors of the form t times 3, 4, where t can be any real number. Okay, so there is the eigenspace associated with this eigenvalue. Okay, there's the eigenspace. And let me just show you a way to have done this just a little bit easier. Is instead of writing this all out, if we would have just subtracted 5 right from the start, if we would have just subtracted 5 right down the diagonal, see right here, right down the diagonal here, we would have gotten 1 minus 5 is 4. There we are right there, 4, 3, and 4, and we subtracted 5 here, and we get 2 minus 5 is negative 3. So we get that right there. So let's do that on the next one. Unfortunately, now I'm running out of space here, so I'm going to have to erase this in order to do the next one. So let me erase this now. And now we will find the eigenspace associated with lambda equals -2. So here's what I'll do. I'm just going to subtract -2 right down the diagonals, right here. I'm going to do it already. And it's going to be 1 minus a -2 is going to be 3. And there's a 3. And then this is a 4. And now I'm going 2 minus a -2, which is 4. And that was all set. That's what you get when you set it all equal to 0. So that's all set right equal to 0. So you can save a couple steps. Let me make sure you're with me again. Yep, you are. And so what do you get? You get 3x plus 3y equals 0. And here you get 4x plus 4y equals 0. Notice that 1 is just a multiple of the other again. So you can get rid of 1. Actually, you can just divide this whole equation by 3 and get that. And you can let y be equal to t. Then x is going to be -t. And so what's your eigenvalue going to be? It's going to be -t, which is t times -1, 1. So this eigenspace is going to be everything of the form t times -1, 1, where t is a real number. Okay? So, you can kind of think of it like this. You kind of think of it that when you take any vector and take the vector, what do you want? Let's say the vector, what does that look like? 5, 2 maybe? I want something that's not here. Yeah, okay. Take the vector 5, 2, and you apply this to it, multiply it by this, you're going to get yourself some other vector that's pointing in a different direction. But you have a couple exceptions to that. Most of the time it's going to send it to a vector which is in a different direction. But if you take a vector along the line 3, 4, which means the x unit is 3 and the y unit is 4. So there you go. There's 3, 4. Everything along that line there, if you take anything, any vector along this line, when I say any vector along that line, take that vector, any of these, any vector like that, and you stick it into here, what's going to happen to it? This thing here is going to take this particular vector, anything that looks like this, and just going to multiply it by 5. So it's just going to give you the same direction. It's just going to be 5 times as big. It's going to either go down there by 5. See that? So that's what it does. On the other hand, if you take anything along the line -1, 1, which means that the x is -1 and the y is 1. So anything along this line, there's that line right there. What happens if you stick anything in there into this thing? What will happen to it? If you take the vector, let's just take the vector. Let's take the vector. I don't care. -2, 2. Let's take the vector -2, 2. No, let's see. -3, 3. Just to keep there being any confusion. Okay, so there's a vector -3, 3. What's going to happen when you apply this to it? I claim that what's going to happen is it's going to take this vector and it's going to send it to a vector which is this thing times -2. So if I take this vector times -2, it's going to end up down here. It's going to end up at +6, -6. That's where it's going to end up. Takes that vector and multiplies it by -2, so it ends up right there. Let's go ahead and do it. So here we have 1, 3, 4, 2, and you apply that to what vector? -3, 3. And what do we end up with? Here we're going to get -3 plus 9 is a 6. And here we're going to get -12 plus 6, which is -6. Is that what I said? Yep, 6, -6 right there. See how that works? So that's the idea. Okay, very good. Okay, so we just have more examples to do now. They're all kind of the same, and you've got lots of them to do for yourself, but this one's a little bit different. So let's find, this is example 10, and then it kind of bleeds over to 15 as well. I have a bunch of things in between, and I pick it up again at 15. So find eigenvalues and eigenvectors for this one. A equals 0, 1, -1, 0. And before we get into this, we're going to get into complex numbers here. So let me just tell you what complex numbers are. Complex numbers, you've heard probably of the letter I, which stands for the square root of -1. So the square root of -1 is denoted by the imaginary number I. Once you have I, then you can combine real and imaginary numbers, and you can go say like 3 plus 2i, and this is on the complex plane now. So 3 plus 2i means 3 in the 3 real part, and then 2 is your imaginary part. So it would be this point right there in the complex plane. And so if you add two complex numbers together, you add them just the way you'd expect. You just add the real parts and you add the imaginary parts, and you just go like that. If you want to multiply two complex numbers together, then you foil it. So here you're going to get 16. Here you're going to get 10i, and there you're going to get 3 times 8 is 24i, so 10 plus 24 is 34i. And then finally you're going to get 8 times I squared. Well, I squared is -1, so it's going to be minus 8. So that's going to end up giving you 8 plus 34i. And I think that's basically all you need to know as far as complex numbers in here. So if you divide, yeah, I think that's all you need to do. So if we need anything more, we'll get it as we need it. Okay, and the book, I cover this material as well. Okay, so let's find the eigenvectors and eigenvalues. So how do we do it? Do it the same way as before. We find the determinant of a minus lambda I, which is going to be the determinant of, what do? We subtract lambdas down the diagonal. So it's going to be minus lambda, 1, -1, minus lambda. So it's the determinant of that. And what's the determinant? It's going to be lambda squared minus a -1 plus 1 is equal to 0. And so if you solve that, you're going to get lambda is equal to plus or minus I. Okay, so you're going to get -1 over, and then the square root of it is plus or minus I. So there's your two eigenvalues. Now let's find the eigenvectors. So how do we do it? So we start off with let's be careful here. So we're going to start with lambda equal I. That's the one we're looking at. And so what do we do here? We take this thing and we subtract lambdas down the diagonal, just like it says here. So it's going to be -I, 1, -1, -I times xy is equal to 0, 0. Which means that -1x plus 1y is equal to 0. And if you multiply this out, you're going to get -x minus I. Minus iy is equal to 0. Okay, now, is it still the case that one of these is just a multiple of the other? Let's check it out. If I multiply this thing by I, I'll get this, right? If I multiply this by I, I'll get this. If I multiply this by I, notice what I'll get. I'll get an I squared, which is -1, and then here's another negative. Negative times negative gives you a positive. So sure enough, one is just a multiple of the other, so I can just get rid of one of them again. And I can let y be equal to t. And again, let me see if I can try to do it. In the book, I let x be equal to t this time. It doesn't really matter. So let x be equal to t. Yeah, if x is equal to t, then you bring that over, and then y is going to be it. And so what's your eigenvector? Your eigenvector is t times 1i. So your eigenspace is, here's the way you do it. It's all the vectors 1i, where t is a real number. So there they all are right there. And you can go through and do the same thing for -I and get the same thing there. So the good news is, this is all the material you need to know from this section. I go ahead and I give you a couple more pages of material just because I think it's kind of neat stuff, just in case you're interested in it. But there's no need. This is where you can stop. You can stop right here with example 15, 7.1.15. and then do the problems that are associated with this, which are exercises 1 through 7, which is what I have so far. Things might change over time, but I'll let you know. Okay, so very good. So that is section and chapter 7.